Lenses. Lenses alter the direction of light, and light can be considered as travelling as waves or as rays. I'll start off by considering it travelling as waves. Here we have a lens, and if plane waves travel towards it, the waves travelling through the centre will be slowed down for a greater distance than the waves travelling at the ends. Therefore, the ends effectively overtake the waves travelling through the centre, and we end up with the waves coming out having curvature, like this. This point here, where the waves are brought together, is known as the focus. This then becomes the focal length, the distance from the centre of the lens to the point at which the light is focused. This is only the focal length if the rays are parallel coming in. This means they're coming from a distant object. The thicker the lens is, the shorter its focal length will be, and we say the more powerful the lens is. The power of a lens, capital P, is given by 1 divided by the focal length. Power is measured in diopters, given the symbol capital D, and this is when the focal length is measured in meters. I'll now consider the light travelling as rays. So rays of light enter the lens from the left and are brought together at the focus. The rays are bent or refracted by the lens. This is a converging lens, it brings the rays together, whereas a diverging lens sends the rays apart, something like this. You'll see the diverging lens is thinner at the middle than at the ends. If we follow these rays back, they appear to have come from this point here. We say there is a virtual image at this point, and the length from the lens to this virtual image for parallel rays is the focal length of a diverging lens. Here we have a thin lens with a focal length of 25 centimeters, the focal length being the distance from the centre of the lens to the point at which the rays of light are brought to a focus when the rays are coming in from a distant object, i.e. the rays are parallel. The power of the lens is 1 over the focal length in meters, which is 1 over 0.25 meters, or 4 diopters. Here we have a thicker lens, and you'll see it brings the rays together closer to the lens. It has a shorter focal length of just 20 centimeters. So the power of this lens is 1 over 0.20 meters, giving it a power of 5 diopters. The lens equation. Here we have a lens with light coming from an object here, forming an image here. If we call the distance to the object u, and the distance to the image v, we would also have the focal length of the lens f, which would be closer than this, as the focal length is where light from a distant object is brought to a focus. The lens equation then tells us that 1 over u plus 1 over v is equal to 1 over f. I'll go through a couple of examples. Number 1. An object is placed 20 centimeters away from a converging lens, and an image is formed 10 centimeters from the lens. Calculate the focal length of the lens. Well, using the lens equation, we can then put in the numbers. U is 0.20 meters and V 0.10 meters. So, using a common denominator of 0.20 meters, we get that 1 over f is 3 over 0.2. So f is 0.2 meters over 3, or 6.7 centimeters. Number 2. A lens of focal length 25 centimeters produces an image 40 centimeters away. How far away from the lens is the object? Well, again using the lens equation, it's now u we want to find. So 1 over u is equal to 1 over f minus 1 over v. Putting in the numbers, then using a common denominator of 2 meters with 8 minus 5 gives u as 2 meters over 3, which is 0.67 meters or 67 centimeters. Looking at how the lens affects the light passing through it in terms of refraction, here we have a ray of light entering the lens. If I add a normal to the surface here, you see that the angle of incidence is greater than the angle of refraction. The light has refracted towards the normal on entry as it slows down. Adding a normal here, you'll see that the angle of incidence is now less than the angle of refraction, and the light has refracted away from the normal on exit as it speeds up. For simplicity, in the diagrams we show the rays changing direction once at the centre of the lens, like this. This isn't what actually happens, it just makes the diagrams a lot easier than doing two bends like this. Let's see how a lens actually forms an image. Here we have a person forming the object and a lens. If we look at the rays of light travelling from different parts of the person's body, first from the head, this top ray meets the lens straight on and so will be bent significantly. The bottom ray is travelling downwards and so will have the same amount of bending but will end up going straight at this point. Light from the centre going to the two ends of the lens will be bent equally and so will end up in the centre. And light from the feet, well, now the ray here is approaching straight on and so gets bent upwards. The light travelling to the top is bent by the same degree but ends up coming out straight. So this point relates to the person's feet, this point to their head. So the image would look something like this. Lenses produce an inverted image. We call it a real image as it can be captured on a screen. Finally, magnification. Lenses are often used to make objects appear larger, for instance in microscopes or telescopes. Here we have an object which the light passes through a lens and becomes larger at this point. If this is the object height and this is the image height, the magnification, given the symbol m, will be the height of the image divided by the height of the object. That tells us how many times bigger the image is than the object. But here we have the object distance u, and here the image distance v. These make up similar triangles, and so by similar triangles the magnification m can be given by the image distance v divided by the object distance u. If m, the magnification, is less than 1, it tells us the image is smaller than the object. I'll now look at a few sight defects. Here we have a diagram of an eyeball with the lens at the front here and the retina at the back. You'll see for this person parallel rays of light from a distant object are brought to a focus before the retina. We say this person has myopia or short-sightedness. The eyeball is too long or the lens is too strong, and the lens brings distant objects to a focus before the retina. By using a diverging lens, the rays are sent outwards before they enter the lens, and so the image is now formed on the retina. So a diverging lens moves the image further back to the retina. In this case, for a near object, the image is formed beyond the retina. We say this person has hypermetropia or long-sightedness. In this case the eyeball is too short or the lens too weak, and the lens brings distant objects to a focus beyond the retina. This can be corrected with a converging lens. The converging lens is starting to draw the rays in for the eye's lens to do the rest. So a converging lens moves the image closer and onto the retina. So for a person with hypermetropia or long-sightedness, they might have an uncorrected near point here, whereas with normal vision the near point would be 25 centimeters from the eye. By using a converging lens, this person has a corrected near point of 25 centimeters. I'll just run through an example of correcting for hypermetropia. A person with hypermetropia has an uncorrected near point of 150 centimeters. Calculate the focal length of lens needed to give them a corrected near point of 25 centimeters. Well, in this case, u, the distance to the object, is 25 centimeters. We want them to be able to see an object 25 centimeters from their eye. The distance to the image is minus, because it is a virtual image, at the opposite side of the lens to where the image would be formed on a screen, of 150 centimeters. We can then use the lens equation as normal, and putting in the numbers, 1 over u of 0.25 meters plus 1 over v of minus 1.5 meters. Putting over a common denominator, we get a focal length of 0.30 meters or 30 centimeters.